Good afternoon. My name is John Erickson. This is Persist, using and abusing Microsoft Fix-It patches. I apologize, my laptop somehow does not work with the system, so I'm going to be clicking this and this at the same time, so it might get confusing. There we go. All right. This is me. It's my Twitter handle. I don't tweet much, but you can follow me if you want to. I'm an engineer at EyeSight Partners. I've been there about 3 years now. I focus on looking at vulnerabilities, exploits, look at malware, and a big part of my job is looking at patches, which is what this talk is about. Every Patch Tuesday, look at Microsoft, Adobe, Oracle, etc. Prior to EyeSight, I was at the MITRE Corporation for 5 years, and before that, I was at in the Air Force and a couple defense contractors. EyeSight Partners is an intelligence threat provider. If you would like more information about EyeSight, please visit our website or come talk to me after the talk. Okay, so here's what we're going to talk about today. Give a little background about what these fixes actually do, some tools they can use to... Damn it. Sorry. Yeah. That was my slide for my company, sorry. And this is what we're talking about today. We're going to talk about some tools that you can use to look at these fix-it patches, some real-world cases where Microsoft has utilized these fixes to prevent exploitation, how I went about reverse engineering this fix-it file format, a simple information disclosure bug you might want to say that I found while doing this, SDB Explorer, which is the tool I wrote during this research, and how you can go about creating your own in-memory patch fix-its, and how you can use that to maintain persistence. Okay, so what are these in-memory patch fix-its? They are a subset of application compatibility fixes. There's a bunch of different names out there. They're called shim databases. They're called app compatibility fixes. Microsoft has a whole website dedicated to these fix-it. It's the Microsoft Fix-It Center. There's thousands out there. They provide a way to modify an application's behavior, how it interacts with Windows. So, for example, if you needed to modify your resolution for some old program, you could have a shim that does that. If you wanted to convert an old Windows NT app to make it work on Windows 7, you might need to change some file locations or registry locations. So you can do that all with these shim databases. And EMIT, Microsoft's Enhanced Mitigation Experience Toolkit, also works via this mechanism. So the first public information I saw on this is from Alex Ionescu. He made a blog back in 2007 called Secrets of the Application Compatibility Database. I guess he intended for it to be a 9-part blog series. He only did these first 4 that I saw at least. He gave a great introduction on the technology, some system shims that are built into Windows, how the shim engine interacts with the PE loader, and he never got to releasing his tool or this bullet here, 7, the runtime in-memory patching behavior and analysis. If he would have released that blog entry, I probably would not be here today talking about this stuff. Mark Badgett presented at DerbyCon last year. He's mainly focused on rootkits and doing penetration testing work, so that's kind of his focus. He wants to do rootkit type things like process execution redirection and API hooking and file system hiding, registry hiding. He showed how you could disable security features of the OS like disabling ASLR or DEP for processes and how to execute backdoors. He showed that you could do all of this through the application compatibility framework that's built right into Windows. It's a very neat work. He did not talk about in-memory patches, which is the focus of this talk, but still cool stuff. So what's the motivation? Why did I want to get started doing this? Patch Tuesday comes out. I diff the patch for IE, you find, for this example here, 465 functions that match. That means you have to look through 465 functions that have, there's differences in them. And are those differences security-related fixes? Are they just normal bug fixes for Windows? It's a hard job. It takes a long time. It takes a long time to just load these DLLs into IDA and run bindiff on them. It takes hours. If you look at a fix-it patch for this particular CD here, there was 2 changes. So within 5 minutes of downloading this fix-it, running this tool, you can see, oh, they changed this assembly instruction from a jump not equal to a jump, or they changed this to hook this function to redirect code somewhere else. Very cool stuff, and that's what got me started in this. Okay, so now let's talk about some tools. There's a few by Microsoft: Application Compatibility Toolkit, STB to XML, and STB Inst, as well as CDD, which we'll talk about briefly, and STB Explorer, which is the tool I created during this research. Damn it. Somebody yell at me if I forget to change the slide, please.
You can look at this monitor.
Thank you. Okay, so the Application Compatibility Toolkit. This is freely available for download from Microsoft. It's a nice GUI tool that allows you to point and click and create nice application fixes. However, I don't think it's very well documented. I've got a couple examples here that I just made up. Pointer. So I created a compatibility fix here called shim via EAT, which means you're going to hook a function via export address table entry. When you create this to the GUI, it's nice point and click, yeah, I want to do a shim via EAT, and then it gives you a text box that says arguments, and it provides no documentation. What's the format for that argument? How do you know? I have no idea. So it was very confusing. They have fixes and they've got modes. Modes are a collection of fixes. So I've got the top one here is a compatibility fix, and the bottom one is a compatibility mode. What I really wanted to point out here is the concept of matching files. And so matching files for IE, it has to match this particular binary version, company name, product name, etc. If those conditions are met, then this compatibility fix will be applied, as well as the bottom. If those conditions are met, that compatibility mode will be set. Now, if we take the same toolkit GUI here and bring in one of these fix-it shims, we see the same matching files entries like we saw in the previous slide. However, there's no compatibility fix listed here. There's no compatibility mode listed here. So how do you know what this does? It has like no concept of what these in-memory fixes are or what they do. So I'm guessing that Microsoft has some internal version of this tool, or maybe they use something a little bit different to create these. Okay. STB to XML created by a Microsoft employee back in 2007, so about the same time Alex was doing his work. This can dump what's called patch bits information. This big blob of base 64 data. You can also have it dump these patch bits section into binary files on disk. Now I'm sorry if it's very small here, but you can see that this kind of has the same information that's provided in the Application Compatibility Toolkit. It's got the application name, it's got the matching file entries, followed by, here we get a little more information. Now there's a patch ref item here. So that means if this matching files entry is met, it will apply this patch ref. And it's got a patch tag ID of 218. But what does 218 mean? I have no idea. This patch up here has no number associated with it. So is that 218, or is it the one that's off the screen right now above it, or the one above that? Or how do you get this linkage of if that blob of unknown data is for this particular version of MS HTML DLL? CDD from Alex, he never released it. He's got this show patches option. Thank you. CDD by Alex, he's got this show patches option. It's not clear if this dumped out the base64 encoded blob like STB to XML, or if it actually parsed out this information in a better format, but never released. Okay, so STB inst, this is a file that's already on your computer. It's a way for you to install STB files. If you go to Microsoft's website, and you can download the MSI to install a fixit. But if you actually extract out what's in the MSI, you'll end up with the STB file. And this tool allows you to install STB files via this mechanism, whether they're STB files that you create using the application compatibility framework or toolkit, or ones that you download from Microsoft. You have to use the -p option when the STB file contains in-memory patches. You have to be administrator to run this tool, and we'll talk about why later. Also, a side effect of this is that these items show up in your add removed programs dialog. And Badgett mentioned in his DerbyCon talk, he's doing all these cool rootkit type things, but then he has to go and see that his rootkit fixit is in the add removed programs dialog. So not very stealthy. So these are the default locations, and this is why you have to be administrator, because STB inst and my tool have to write to these two registry locations, HKey local machine, custom, and installed STB. And so what you'll find if you look at this location, custom, you'll find entries for applications that have shims applied. So you might find one for iExplore.exe, or for WinWord, or for Outlook, or any other program that may have had a in-memory fixit installed one time. This is also where you'll see applications that have emit applied to them. Under the entries in custom, there'll be a GUID. You follow that GUID under the installed STB folder, and you'll find information like this. This shows you the description, which is just a comment. It'll show you the database timestamp, the location on the file system where that STB file exists, and the database type, which in this case, this flag just means it's a shim database type. Okay. I got bored and I played around with animations, and that's all I got. So this is kind of like my my cab ride from the airport here. It's pretty exciting. So this is my tool for installing. I'm going to talk more about my tool later, but you give the -r option with the STB file that you've got, and you give you an application name that you want to shim. This does not show up in the add remove programs. It does not copy the STB file to the default locations. I should have mentioned back here actually. This is the default locations that the STB inst program copies the file to. So if you're installing a 32-bit patch, it's going to put it in the app patch custom directory. And if you're installing a 64-bit patch, it's going to put it in the custom 64 directory. My tool does not copy into these default locations, so you need to be aware of if you're making a patch for a 64-bit program, you need to have custom 64 somewhere in the full directory path. That's how Windows checks to see if you have got a 32-bit or 64-bit patch. It just checks based on this directory name. Okay, so let's talk about some real-world cases where Microsoft has used this. The four most recent that I've seen using the in-memory fix-it type are these. Just a quick note, in the news this week, Microsoft put out an advisory about an RTF vulnerability, and in their security advisory, they mentioned a fix-it patch that will help prevent it. That's not an in-memory fix-it patch. That will just disable Word opening RTF files, essentially, or processing them. So they don't do an in-memory patch. So these top three are IE vulns. The bottom one was a XML core services bug, and in all these cases, the fix-its were actually targeting IE. So XML core services is a system-wide library used by many applications, such as Word and Outlook. But Microsoft just released the fix-it to protect IE using that library, not other ones. And we're going to focus on this most recent one for the rest of the talk. So this was publicly disclosed by FireEye on February 11th, being exploited in the wild. Microsoft released a fix-it on the 19th, so that's 8 days. They already had a fix-it out the door, which is great, so that you don't have to wait till the next patch cycle of Patch Tuesday to be able to protect your enterprise. Again, using my tool, which we'll talk about later, this -D option will essentially print out all of the matching file entries within the database. So this particular database file, there was 8 different entries that they were targeting. These versions of IE with these PE checksums. So IE 9 and IE 10. And just a note on that, if you didn't have the latest versions of these DLLs and installed the fix-it, it does nothing for you. You have to have these exact versions for this fix-it to help you. Otherwise, it does nothing. So let's start talking about how we can figure out what this does. Now, when I first started research into this, I didn't actually know about this this extension to WinDbg that I'm showing here. And so it was a kind of a manual process. I loaded up IE, I did a memory dump, I installed the fix-it patch, I loaded IE again, did another memory dump, and then did a binary compare of the two outputs to figure out where the bytes started, where were they different, essentially. And it was a pain in the butt. And this plugin here for WinDbg was very helpful. So if you want to play along at home, this was the DLL that I had running on my system when I ran these commands. And what we see here is before the fix-it, there's no corruption. That's what this tool calls corruption or differences, essentially. And so if we see this memory range here, there was a 5-byte corruption. If you've got symbols installed, you'll see that this was within the insert text internal method. And the expected 5 bytes are those, and the bytes it found there were those. And there's a second one. Now I've disassembled what those 5 bytes are, the new 5 bytes are down here, and we can see they're both jump instructions. And I don't have it on the screen, but if I would have showed the disassembly of the before fix-it installed, you would see that it's a standard function prolog, just a move edi, edi, push EVP, etc. So they're essentially hooking these two functions. And we're going to talk about these bytes later, so I bolded the things that I'm actually going to focus on later. The address here ends in 70EF. There is a 5-byte corruption, and if you can remember those 10 bytes, remember them. Otherwise, I'll remind you later. Okay. So what does this fix actually do? If we look at what does that jump do, we see where it jumps, we disassemble that code, and we can see that Microsoft has, saved all the registers, called some additional function, restored the registers, and then it will return back to where the jump came from. This particular function additional function that they're calling increments a reference counter. And this is a use after free bug, so they are making sure that they always increment this reference count. Microsoft actually wrote a blog about this, and they say, we know that this produces a memory leak because we're never freeing this memory, but at least it's preventing the vulnerability from being exploited, because we avoid the free, don't let it ever free. One other thing that I wanted to point out, this other code here did not show up in the check image output as a corruption. And we just saw the two jumps, not this additional code. And the reason for that is the check image extension only considers code in the original image size. So any bytes that are outside of that image size are not considered for potential corruption. So basically Microsoft went to the end of executable code, wrote this additional code, and then just put a reference to it to jump to it. Okay, so let's continue on this quest of reverse engineering, figure out how this patch bits format's processed and how the payloader handles it. A couple slides ago, I highlighted those bytes in bold for you. This number 5 is it's little endian, so it's least significant bytes first. So that's 5 was for 5-byte corruption. We see the EF70; those were the lower 16 bits of that address. We see these are the 5 bytes where the expected 5 bytes. This is another 5 followed by EF70. For some reason, I don't have that boxed. And then these are the 5 bytes that are now corrupting those original 5. So this is a kind of a general idea, and let's see how Windows actually parses this information. Oh, I should say that this dump of hex right here, if you go back to the STB to XML tool and grab out that base64 blob, that's what it looks like. It's just these bytes. That's all I did there. Okay, so how does, here's a very high-level view of what the payloader does when it's applying an in-memory fix-it. It initializes the shim engine. It resolves a function within the app-help DLL called SE-DLL loaded. SE stands for shim engine. Within that function, it calls patch new modules, attempt patches, and an apply patch. And the apply patch function is the one that actually does the work of processing this patch bits information. Okay, so here's some pseudocode representation of this function. It takes a pointer to a patch bit structure. This is a structure I came up with, so that's my name for it. I don't know what Microsoft calls it. But essentially, it's just going to iterate through all of, I kind of call them patch actions. And a patch action can be either a match or a replace action. So if it's a match action, it's just going to do a mem compare of the pattern specified for some module base plus an RVA for that pattern size. If it matches, it continues along just fine. Otherwise, it returns out. If it's a replace action, it's going to change the memory permission of the area specified. So it will go to that RVA for the number of bytes specified. It will make that memory read-writable. It will then copy the bytes that you want into that new memory area and then restore the permissions back to original. So read, execute, or whatever they were. And then it flushes the instruction cache. It'll continue to do this until it gets to the end, essentially. So along with the SCI apply patch function that we were just looking at, the appelt DLL has 195 exports. Microsoft has documented them somewhat at this location. They don't provide any header files for you to use or a library to link against. So it's kind of a manual process to create those. The code that I'm releasing has all that header information in there for you with all the function names, and so it'll save you some time. This library can be used to read and write or create STB files. The documentation is definitely lacking. It's been lacking for many years. Like in 2007, Alex was talking about it lacking information. So one problem I was having with it was I want to extract out that patch bits area, which is a binary field, and you're required to give this function a buffer and a buffer size. And I'm thinking, well, how do I know how big this patch bits area is? Where do I figure it out? And I'm staring at this documentation from Microsoft for hours. Nothing's coming to my mind. And finally, I just brought up STB to XML and IDA and figured out how do they do it. And they're using this undocumented function called get tag data size. And that will give you the size you need. This API does not contain the code to actually parse out what these in-memory patch bits areas are. So that's something we're going to get to. So the STB files themselves are binary files. Here's a very simple YAR rule if you guys are searching for files on your computer. You'll find a lot. There's a lot of default STB files on your computer. They are STB files that are packaged with installers for old games to make sure that the resolution's set right. So this will get you a lot of crap by using the signature. So it might be better to modify this to look for not only this magic string STBF, but also look for these files that contain a patch bits tag ID within them as well. So that's something that if you guys are interested in, you can do. So here's the structure that I came up with. First, there's match operations and replace operations, 4 and 2 respectively. You've got an opcode, which is either a match or replace. You've got the action size, which is the total size of this structure. The pattern size, so the number of bytes you want to search for or replace. The RVA, and then a module name. Now if we take that and apply it to that same hex dump and kind of overlay it, we get to start make some sense out of this data. So we see it starts with the number 4, which is for a match. We see 59 is the size of the first action. So if we go to offset 59 in here, we see it's a 2, which would be a replace. So we know that it's just patch bits or patch action after patch action. 5 was that 5 that we had highlighted before, which is the number of bytes to search for. This 4 bytes here is an RVA. And then here is the module name, which is null terminated. And then after the module name, which is this pattern to search for. You'll notice that there's this big block of crap, I'll call it, from here to here that contains just random data. And this is kind of what I'm talking about with the simple information disclosure. And so that the module name field is a fixed length of 64 bytes, so 32 characters. It contains uninitialized data from Microsoft's tools that they use to create these fixits. They don't zero it. I've told them about this, and they released this last one, and it still had uninitialized data, so I don't know if they really care. I I added an option to my tool, this -L, and it will go through and grab all that uninitialized data out of each patch action and save it to a file for you. I've done that for the 4 fix-it that I've mentioned at the beginning. I didn't find anything useful, but maybe someone can get something useful out of it. I don't know. It's either stack or heap data in whatever tool that Microsoft uses to create these things. So it's kind of neat, but the fix patches that are created using my tool, I make sure to zero this out. So I've mentioned it a few times. Let's start talking about my tool here. I've already mentioned how you can go about installing STB files with my tool, how you can print match entries, and how you can dump this leaked memory. So we're going to focus on what I call printing a tree, printing out the patch details, and creating patches. So this is the print tree option. It's -T. And this prints very similar information to STB to XML. But there's a couple additions. Besides, it probably looks ugly. On the left of each tag is a tag ID, followed by tag, and this tag code here, 705 means patch, 60001 means name. Those numbers there are documented by Microsoft, what they made. But what I think is cool about this is now, this is the same information we had before with Internet Explorer, the matching file entries, and then the patch ref we see is 218 or hex DA. Now we see that this is actually DA up here. So now we have that linkage between a particular match entry and the associated patch bits area, so we can tie the two together. To view patches, you need to use one of these 5 things, either a patched ID or a patch bits ID or a patch ref ID or a patch tag ID or checksum. And so I've highlighted them on this slide here. Oops. So the tool has 2 different options for displaying patches, P and S. P you use for all those patch tag IDs that I was talking about before. S you have to use with the checksum. Excuse me. So this displays out the information nicely. It shows you the module that they're targeting, the particular action, whether it was a match or replace, action size, pattern size, the RVA where this is at, and then the bytes. So this is going to do a match operation at the RVA, these bytes, and then I show the disassembly of those 5 bytes, that's just the standard function beginning. And then the second action here was a replace action, that RVA, and makes it a jump. And that's the same thing that we saw using the check image extension. Now this, if you give the -I option, this will dump it in a IDA Python script format. I was originally writing a IDA plugin for this, and I found the process not fun, and I was running out of time, and I ended up just making this happen real quick. So basically, you bring in the module that you care about into IDA. You run this tool against your STB file, copy and paste this into IDA, run it, and this will print in the console window that it's patching so many bytes at some address. And then you can either go into your patched bytes menu, or you can just double click in the console window and it will bring you to the associated code regions where this happens. And so we can see here that these 2 small ones that's just applying that hook, that's making the jump. And these big lines here, that's where it's putting the additional code at the end of the image. Okay, so let's talk about how we can create our own fix-its. Required information, you need a target. You need a target module or modules, so that could be a DLL within the application that you're targeting, or it could be the application itself. And a requirement because of that fixed length field is that the name has to be less than 32 characters. So 31, and it needs to have that null terminator at the end. You need to know the RVAs that you're targeting for either match or replaces, and the bytes that you want to put there. It's implementation specific. So I created a config file that my tool processes to create these. They have to begin and end with these, tags that I have. You specify the application name. DB name could be anything. That's what will end up. That will end up in your registry. When I showed the screenshot before, there was one that looked like a comment. It was CVE, XYZ. That's what will show up in DB name. You can have some comments, and there's really three things you can do. There's P, R, and MR. So P will define a new matching files entry. And so within a matching files entry, all I allow you to do is give a target module, which can be a DLL or some type of image name, and optionally you can have a P checksum. Within a P tag, you can have R or MR. R does a replace action. I think looking back, I probably should have called this a write action. It makes more sense, but when I originally did this, I called it replace, so it's all over the place now. It makes more sense to just call it write. So write, you have a target module again, the RVA, and a hex string of bytes that you want to write to that particular RVA. MRs does match replace combo. So you give an RVA, you give your hex string that you want to search for, and then the hex string that you want to write there. Okay, so I created a sample target that we can go after. This is included in the GitHub repository. Basically, this code loads MS-HTML DLL. It does get proc address for this exported function per HTML. Prints out the RVA for you and prints out 15 bytes of memory starting at the RVA minus 5, and then prints out the disassembly for you. So it gives it some target. Now, I took that same screen from the prior slide, put it here, and I've got a sample configuration for this target program. I hope you guys can see this okay. But again, you have your application name, some type of comment. Then I wanted to target this MS-HTML DLL within this target application. And I want to do a match replace action for this DLL at this RVA, 50B. That's here, 50B. I'm going to look for these opcodes, which is what I've got listed here, and I'm going to replace that with CCCC. Then I'm going to do a replace action for that same DLL at 506, which is up here at the beginning, and I'm just going to put the bytes 1, 2, 3, 4 there. Using the tool, you give the -C option with the configuration file that you've created, and -O to just give an output name for the STB file that you're creating. Now this processes the config file. It prints out some debug information. This was really for me, but it may be useful to you guys while you're doing this as well. Then we take this STB file, we go back to the program again and run it with the -R to install it, or we use STB inst if we don't care about the add remove programs thing, and we install it in the system. Then when we rerun sample target, we can see that at offset B, there is CCCC. So it properly did the match and replace, and then we can see that it did overwrite at 506 with 1, 2, 3, 4. And the disassembly there doesn't really make sense because 1, 2, 3, 4 is something weird. So how does this all work? Whether you double click on something, whether you run something from the command line, it's the parent process's job to do a create process, which calls create process internal, and the create process internal determines if the target needs to be shimmed. It goes to the registry, to that custom folder. It looks, does this image name match what I'm about to run? Then is there an associated shim database file for this application? If it does, it sets some loader flags and lets the child start up. The child's P loader looks for a flag that's set and determines if it should attempt to look for shims. So yeah, it uses this to determine if it should look for shims. So if it's there, it will do that same, go to the registry, am I a target? Yes, there's an STB file for me, apply it. This is kind of very vague what I'm saying here, but Alex gave some details about how this works, so you should read his blog. So for debugging this, you can set this environment variable here, and this is output from sysinternal's debug view. And it's kind of small, I apologize, but I'll just point out a couple things. It has the application name here at the beginning. This says st.exe. Just think of that as sample target. Then it clears some flags that was set. Then it attempts to do a patch. And it fails because MS-HTML DLL has not been loaded yet into the process memory space. Later on, we see SE DLL loaded, says, hey, I finished loading MS-HTML DLL. Then SE I apply patch actually does the action. It does the writes, it does the match, it does the writes. And it says, yes, I've successfully applied one of one patches. So now let's talk about maintaining persistence. So very simply, we can just target explore.exe, patch winmain, hook it to create process calc. So this is a sample config file for Explorer Win7 64-bit. You give a P entry for explore.exe because it doesn't have to be a DLL. I gave it a specific P checksum that I care about. This RVA here is for winmain, and I overwrite the first bytes with a jump. Then this is at the end of the image size. That's just my shellcode. Included in GitHub is the configuration files for Win7 32-bit, 64-bit, and Win8 32-bit. So if you took this, used the tool with the -C, and then get the output from the IDA Python script, load Explorer into IDA, this is basically what you'll see. So before the fix it, after the fix it, it just has that jump instruction. That's all I'm doing. If you follow that jump, this is my shellcode. I don't write shellcode for a living, so don't laugh at it. Basically, I save all the registers, I call create process, restore the registers, and jump back to main. So what can we do about this? You can disable the shim engine. You can do it through group policy. I don't recommend doing this. It will break emit. It will basically make these zero-day fixes that Microsoft releases pointless. But it is possible. There's probably some other unintended consequences of disabling it. You should search your registry and file system for STB files. These are YARB provided. Your system is going to have STB files. They're normal. They're not all bad. There's lots of good ones out there, but you can use the knowledge you gained today, how to use some of these tools to be able to figure out what are these files actually doing on your system. And then you can focus on, okay, I know all these are normal. This one doesn't look normal. What does this actually do? Auto runs from sysinternal's does not consider application compatibility fixes as a persistence mechanism. So whether they're something like I created here, this in-memory patch fix it, or some of the things that Mark Badgett talked about, System Controls does not consider it. I told Microsoft that they should add signature support to STB files. My copy of Explorer is signed, but yet it lets me have my unsigned code patch it in memory and do weird things. So maybe they should let us know that some non-signed STB file is running or about to run. And this is a feature. This is not something that's making you more vulnerable having this default on your system. Someone needs to be administrator on your box to install these. So if they're that far, you're already owned, but this is kind of just a new way that you might not be considering how they're maintaining persistence on your system. And this third bullet is really what I think is awesome. This provides a great opportunity to figure out what Microsoft is doing fixing things. It's so much easier to look at 2 changes versus hundreds of changes to try to figure out what Microsoft did to try to prevent exploitation. And I don't know if I mentioned this earlier, Exodus Intel guys looked at some fix-its. I can't remember which one it was off the top of my head, but they showed within probably a day or a couple hours probably that the fix-it that Microsoft provided for something was totally insufficient, that they could find a way around that to continue to get code exact. So now you guys should know about these tools which will help you do your analysis. So here's some references. If you guys are really interested in this, you should read the paper that's on the conference CD. Lots of good information there. Thanks to my wife and friends. My wife and I just had a baby last week, 1 week old, and I had to leave, which kind of sucked. So thank her. Thanks to Microsoft, iSight, and Black Hat. And this is how you can reach me, my email, Twitter, and this source code link, this is not on the conference CD, so you can take a picture or send me an email and I'll send it to you later. And I don't know if we've got time for questions or not. Anyone have any questions? The question was, does the in-memory patch invalidate the signature as shown by Process Explorer? And I don't know the answer to that question. I would guess no. Anyone else? Go ahead.
Do you have any plans to make either what is with STB Explorer? I think it's more convenient to analyze patches in either Pro than use the special brother tool.
Right. So the question was, do I plan on continuing to work on the IDA Pro plugin? And probably not. And I don't think these happen often enough where it's worth my time to try to develop one. I thought it was a very painful process to do. It was my first time ever trying, and I've got better things to do. Anyone else? All right, well, thank you. If you've got anything else, you can come up and see me after.